All right, today what we're going to look at is polar graphs and area. Now, most of the time with polar, you do not get a calculator on the AP exam, but we're going to use our calculator just a little bit to see what's going on with these graphs. So this is just kind of a visual part of it. You really don't need the calculator to be able to find your answers. So it says find the angle, for example, 1, find the angles where the petal begins and ends. So if I go to my calculator, let's get it started, and I want to go to mode, and I am going to go down here to function, and I'm going to put it on polar mode. Okay, so that is going to allow us to see a polar graph. So when I go to y equals, it's not going to have y, it's going to have an r. So if I type in 2 cosine 3 theta, and it's going to put a theta instead of an x, and let me see, let me do my window from theta min to theta max would be 0 to 2 pi, and I'll just leave it at negative 10 to 10 and negative 10 to 10. And I'll graph. So there is my, let me zoom in a little bit. Let's change my window. Let's go negative 5 to 5 and negative 5 to 5. So that's a little better. Okay, so there is my graph of my polar equation. So what we're asking for is we're asking for where one of these petals begins and ends. Well, if you think about it, they begin and end when they touch the origin, which remember is where what we call in polar the pole. Sorry, I lost the word there for a minute. And the pole is where the radius is equal to 0. So in order to find where a petal begins and ends, we want to know where 2 cosine 3 theta is equal to 0. So we're just going to solve for theta. So if I divide by 2, I have cosine of 3 theta is equal to 0. Well, cosine is 0, so 3 theta is equal to 0 at pi over 2 and 3 pi over 2. And then I'm going to divide by 3, so theta is going to be pi over 6 and pi over 2 and so on and so forth. So that would be a pole would begin at pi over 6. A petal would begin at pi over 6, and there'd be another one that began at pi over 2, and so on and so forth, okay? And a lot of times, if you watch the graph, it doesn't mark out, they don't go in order, okay? So when we graph this, we probably are not graphing this petal on the right first, okay? We're probably graphing something else first, but that's when we'll begin and end with a petal. That's what we need. All right, so if we have r equals 3 sine 2 theta, okay, so if I go graph this one, so if I do 3 sine 2 theta, and if I graph it, so now we have, again, something that looks like that. So a petal begins and ends when we hit the origin, which would be when our radius is 0. So 3 sine 2 theta is equal to 0. So sine 2 theta is equal to 0. So 2 theta is equal to 0 and pi, and so theta would be equal to 0 and pi over 2, and so on and so forth, okay? So that's what we're looking for, because what this is going to do is it's going to lead us into how to find polar area, okay, and how to find the bounds on a polar area problem. All right, so the next thing we need to know is find where the two graphs intersect. So if we graph them on the calculator, the first one is r equals 1, the second one is r equals 1 minus cosine theta. If I graph those, you can see that they intersect, and if I look at the graph, it looks like they intersect at pi over 2 and 3 pi over 2, the positive y-axis and the negative y-axis. Can't talk today. But let's see. So to find where two graphs intersect, we set them equal to each other. So we have 1 is equal to 1 minus cosine of theta. So if I move my 1 over, I have 0 is equal to negative cosine of theta. Change my signs, so theta is equal to pi over 2 and 3 pi over 2, which is what it looked like on the graph, okay? All right, and again with this one, we would set them equal to each other. So 3 plus 2 sine theta is equal to 2. So 2 sine theta is equal to -1. So sine theta is equal to -1/2. So that would be in the third and fourth quadrants. So that would be 7 pi over 6 and 11 pi over 6. Now, if we were to graph those, let's see what it looks like on the graph. We would have r equals 2 and r equals 3 plus 2 sine theta. All right, and there they are in the third quadrant and in the fourth quadrant. So, and again, you've got to remember that when we're in polar, this is no longer horizontal and vertical movement. This is movement around in a circle, okay? Think about a clock hand sweeping across counterclockwise and the clock face. So this is the angle measurement 7 pi over 6, and this is the angle measurement 11 pi over 6. All right, we want to find where the inner loop begins and ends. Now, what am I talking about with the inner loop? Well, if I graph this, I've got 2, let's see, square root 3 plus 4 cosine theta. And if I graph that, well, it's hard to see, but inside there, if I zoom in a little bit, let's change my... -2 to 7. Okay, so if I graph it, can you see that little inner loop in there, that little hole? I know it's hard to see. I'll move it closer. See that little hole in there? That's what we're looking for, okay? We're going to look for where that begins and ends. So again, that begins and ends when the radius is 0. So we have 2 square root 3 plus 4 cosine theta is equal to 0. So 4 cosine theta is equal to a -2 square root 3. So cosine theta is equal to negative square root 3 over 2. So theta would be, let's see, that's the pi over 6 family in the second and third quadrants. So that would be 5 pi over 6 and 7 pi over 6. So that would be 5 pi over 6 would be basically coming along right here. And then 7 pi over 6 would be coming along right there. Okay, does that make sense? All right, and then if we do one more, we've got, let's see if this one is easier to see. 2 minus 4 sine theta. Yeah, oh, let me recenter, let's see. So let's go -5 to 5, but let's do 3. That should be good. There we go. All right, see how big that inner loop is now? That's what we're looking for, is that little guy right there. So again, it starts and ends when the radius is 0. So 2 minus 4 sine theta is equal to 0. So -4 sine theta is equal to -2. Sine theta is equal to 1/2. So that would be in the first and second quadrants. So theta would be pi over 6 and 5 pi over 6. Okay, and again, if you think about those angle measurements, pi over 6 is going to be like this guy right here, okay? And what's happening is we have a negative radius. This is where the radius is negative. So pi over 6 is right there. 5 pi over 6 is right there, okay? So there are your angle measurements. Okay. All right, so how are we going to use all of that? Well, the reason or the point behind that is because we now need to find polar area. We need to find the area of this shape. And so area comes from an area of a sector. And so area of a sector is pi or theta over 360 times pi r squared. This is theta is the portion of the circle that we're using, that we're looking for, times the area of the entire circle. So that would be like a fourth of the circle, or a half of the circle, or 5/8 of the circle. And if we translate that into radians, then it becomes theta over 2 pi times pi r squared. Well, what we want to do, just like with rectangular and Riemann sums, is we want to turn that theta and we want to make it smaller and smaller and smaller. And so that theta becomes our d theta, okay? And so this is the formula that I remember. It's 1/2 the integral from alpha to beta of r squared d theta. This is just in function notation, okay? But I just remember this guy. So it says find the area bounded by the following polar equations. So we have r is equal to 5 sine theta. So here is my 5 sine theta. Now this one is just a little bit tricky, because if we look at 5, well, we already have a graph of it, but if we do 5 sine theta, this one, if we go from 0 to pi, well, that's the whole circle. Okay, so this one, it only takes pi to mark out the whole circle. Okay, so we want to find this area right here. So we're going to do 1/2 the integral from 0 to pi of 5 sine theta d theta. Oops, I need to square that. Squared d theta. So that's going to be the area, and we're only going to set these up. You can use your calculator to figure them out later. And your calculator does not need to be in radian modes to to calculate the area, although it can be. It doesn't matter to me. Okay, so circles are a little bit tricky because our theta goes from 0 to pi. All right, for this one, it says find the shaded region of r equals 1 minus cosine 2 theta. So we want to know where our radius, because we only want to know this part right here, we want to know where our radius is 0. So that's why we practiced that before. So to find our radius is 0, we're going to do 1 minus cosine of 2 theta equals 0. So that would be what? Cosine of 2 theta equals 1. So that would be 2 theta is equal to 0 and 2 pi. And so then theta would be 0 and pi. Now that kind of makes sense, because here is your angle 0 and here is your angle pi. And so what we're doing is we're mapping out this little area right here, okay? And that's what we need. Now, a lot of times in AP land, they like to use symmetry. So while we could go from 0 to pi and get the whole thing, we could also go from 0 to pi over 2, get half of it, and then double it. And that's probably what you would see on a multiple choice question from College Board, is you would see 2 times 1/2 the integral from 0 to pi over 2 of my r squared d theta. So 1 minus cosine of 2 theta squared d theta. And then the 2 and the 1/2 would cancel out, and so you would only just see the integral from 0 to pi over 2 of 1 minus cosine of 2 theta squared d theta. And that is what would be, a lot of times these are multiple choice, and that is what would be on the multiple choice section of the area. You don't really calculate it, you just do it, set it up. All right, so this one we want the inner loop of the limacon 2 cosine theta plus 1. Okay, now to find the inner loop, our inner loop is when our radius is less than 0. So we need to find out, we're going to have to do a sign chart for our radius. So we're going to take 2 cosine of theta plus 1. We're going to set it equal to 0. That would be cosine of theta is equal to negative 1/2. So theta is equal to, let's see, that would be 2 pi over 3 and 4 pi over 3. 4 pi over 3, third quadrant. All right, so I'm going to do a sign chart for those two guys. So here's 2 pi over 3. Here's 4 pi over 3. All right, now there is no, it's going to alternate, okay? So there is no doubling up where it doesn't alternate. So if we pick an angle between 2 pi over 3 and 4 pi over 3, let's say pi, okay? So we pick an angle pi and we plug it in. Cosine of pi is -1. That'd be -2 plus 1. That would be negative. So if that's negative, then these two are positive. So what's going on is the inner loop is happening between 2 pi over 3 and 4 pi over 3. So if I graph 2 pi over 3, that's going to be this guy right here. And if I graph 4 pi over 3, that's going to be this guy right here. So what's happening is when we plot the points between 2 pi over 3 and 4 pi over 3, we're really plotting this little piece right here, okay? So that's what we want to find the area of. So that's going to change our bounds. So we're going to set up our integral. Now, if we use symmetry, halfway in between that is going to be pi. So if we do symmetry, let's see, let me do it in a different color. We're going to have 2 times 1/2 the integral from 2 pi over 3 to pi. And then we're going to take our equation, 2 cosine of theta plus 1 squared d theta. And that's going to be our integral to find our area of that inside loop, okay? So if we cancel that out, it would be the integral from 2 pi over 3 to pi, and it would be 2 cosine theta plus 1 quantity squared d theta. All right, next one, it says where one petal of the rose curve r equals 3 cosine 3 theta. So we want to find the area of one petal. So let's see. Remember, we've got to find where the radius is equal to 0 first. So 3 cosine of 3 theta is equal to 0. Cosine of 3 theta is equal to 0. 3 theta, is equal to pi over 2 and 3 pi over 2. And so theta is equal to pi over 6 and pi over 2. So those are going to be our bounds. Now, what happens is what we're marking out, believe it or not, when we do this, pi over 6 is this guy right here, and pi over 2 is this guy right here. So what we end up, sorry, I'm turning it around so much. What we end up doing is tracing out this petal. Now, it doesn't matter which petal we're using because they're all equal. So we're going to be using this petal right here. So to find my area, and I'm not going to do symmetry on this one, it's going to be 1/2 the integral from pi over 6 to pi over 2 of our formula 3 cosine 3 theta squared d theta. Okay. All right, what do we got next? Next we have inside area region inside the outer loop of the equation. So this one is easy. If we want the outer loop, then we're just going from 0 less than or equal to theta less than or equal to 2 pi. So we won't have to use the symmetry. We'll just do 1/2 the integral from 0 to 2 pi of 1 minus 2 cosine theta squared d theta. That'll give us everything inside there, okay? And then next, find the area inside theta plus sine 2 theta. Now, this is what the AP likes to do. They like to give you this kind of weird shape, but they're giving you the bounds, and you can look at it. Here is 0, here is pi. So as you sweep across from 0 to pi, you're getting all of this area. And there is no symmetry that we can use here because this is not a symmetric curve. So my integral is going to be 1/2 the integral from 0 to pi of r squared, which is theta, plus sine 2 theta squared d theta. So a lot of times area on the AP exam, if you remember your formula, is pretty easy because they give you the shape and they give you the bounds and you're just plugging it into the formula. All right, a couple more. It says find the area of the region inside the outer loop and outside the inner loop. So now what we want is this region here. Let me see, let me do this in green. Is this region here where we have left the inner loop open. So this is we're gonna have to do some subtracting here. So I'm gonna find the area of the entire region and then I'm gonna subtract the area off of the inner loop. So in order to do that, I need to know when the inner loop happens. So I'm gonna take my 2 plus 4 cosine of theta, set it equal to 0. That would be cosine of theta equals -1/2. So theta is equal to, let's see, that would be the pi over 3 family. So that would be 2 pi over 3 and 4 pi over 3. All right, if I were to graph those angles, let's see, that would be 2 pi over 3. And this would be 4 pi over 3. So doing a sign chart for that, let me do it right here. I know I'm writing sideways. All right, and then 4 pi over 3. Okay, so what have I got? If I do pi in between there, pi would be -1, that'd be -4 plus 2, so that would be negative, so these would both be positive. So my inner loop is right in here. Okay, so I am going to do the area of my entire, they're called limacons. I'm going to do the area of my entire limacon, so that would be 1/2 times the integral from 0 to 2 pi of 2 plus 4 cosine theta squared d theta minus, now I'm going to do the area of the inner loop, and I won't bother to use symmetry. So it would be 1/2 the integral from 2 pi over 3 to 4 pi over 3 of my same formula, 2 plus 4 cosine theta squared d theta. So that would be the area of the outer minus the inner. Okay. All right, last one, we want to find the area enclosed by 2 loops of the polar curve. So we're going to find one loop and then just double it. So if we've got 4 cosine 3 theta, we want 4 cosine 3 theta equal to 0. So cosine of 3 theta is equal to 0. 3 theta, I feel like we've done this already, is equal to pi over 2 and 3 pi over 2. So theta would be equal to, I guess, I don't know why I keep doing comma, would be equal to pi over 6 and pi over 2. So we're going to do 2 times 1/2 times the integral from pi over 6 to pi over 2 of the formula for cosine 3 theta squared d theta. Okay, so then I can cancel those guys out. So they like to use symmetry because they like to cancel out the 1/2. All right, so that would be finding the polar area of a curve. You've just got to remember that your formula is 1/2 the integral from alpha to beta of r squared d theta. Next, we're going to get into finding polar area of multiple curves, which does get a little bit more complicated, but for the most part, this is your basic polar area. All right, if you have any questions, come see me, guys. Bye-bye.